Welcome to our video on Chapter 5, Work, Energy, and Power, based on the CBSE Class 11 physics curriculum. We will explore the fundamental concepts of classical dynamics, including the work-energy theorem, conservative and non-conservative forces, potential energy, and the laws governing collisions. In this first part of our video, we will cover the necessary mathematical prerequisites, focusing on the scalar dot product, the fundamental notion of work, and key relationships in rectilinear kinetics. Let's begin with the scalar, or dot, product. Geometrically, it represents the product of the magnitude of one vector and the projection of the other along it. It follows the commutative law and is distributive over addition. In Cartesian coordinates, the dot product is calculated component-wise. The work-energy theorem is a core principle in physics. It states that the net work done on a particle is equal to the change in its kinetic energy. Kinetic energy itself is a scalar measure of an object's capacity to do work based on its velocity. In physics, work is formally defined as the dot product of force and displacement. Interestingly, work is zero in three specific scenarios: when there is zero displacement, when the net applied force is zero, or when the force is perpendicular to the direction of motion. In part 2 of this video, we shift our focus to more complex scenarios, including variable forces analyzed through integration, the nature of conservative fields, and the law of conservation of mechanical energy. When force varies with position, we calculate work by integrating the force over the displacement. Geometrically, this work done is equal to the area under the force displacement curve between the initial and final positions, which remains consistent with the work-energy theorem. Potential energy is stored energy resulting from an object's position or internal configuration. For conservative fields, work done against the force is stored as potential energy. Notably, the force is equal to the negative derivative of the potential energy with respect to position. Total mechanical energy is the sum of a system's kinetic and potential energies. If only conservative forces are involved, this total energy remains constant. We also apply these principles to understand the dynamics of objects in a vertical circular loop. Next, we examine the potential energy of an ideal spring. According to Hooke's law, the restoring force is proportional to the displacement. Integrating this force reveals the potential energy stored in the compressed or stretched spring. Power quantifies the rate at which work is performed. Instantaneously, power is the dot product of force and velocity. We also look at common units for power and energy, such as the watt, horsepower, and the kilowatt-hour. Collisions are classified by how momentum and kinetic energy are conserved. In elastic collisions, both are preserved. In inelastic collisions, kinetic energy is not strictly conserved, often dissipating as sound or heat. To summarize this chapter, remember that the dot product is your foundation. Use the work-energy theorem to link force to motion and apply energy conservation principles to conservative systems. Pay close attention to these topics, as they are frequently tested. This slide provides the image source for the spring mass system diagram used in our discussion. This final slide lists the source for the additional image used in this video.